Hello, everyone, and welcome to today's webinar, Mechanical Comparisons of Electrical Insulating Materials. My name is Mike Moran. I'm the Vice President of Business Development and Engineering at the Gun Company, and I will be your host for today's session. First, I would like to thank everyone for taking time out of your busy schedule to attend today's webinar. Before we begin, I want to cover some basic housekeeping tips to maximize the value of your webinar. To ensure the best connection possible, please close out any programs or apps that may be eating up a lot of data in the background to free up your bandwidth space. You can join the audio using your computer. However, if you would prefer to join over the phone, just select telephone in the audio pane and the dial-in information will be displayed. This will also help clear up some bandwidth. Your audio settings will be set to listening only for the presentation portion of the webinar. You will have the opportunity to submit text questions to today's presenter by typing your questions into the Q&A pane of your control panel. You may send your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Any unanswered questions will be followed up via email following the presentation. If you would rather ask a question directly rather than type it in, raise your hand and we will unmute you. Today's webinar will be recorded and available on demand, and a link will be sent out to all attendees within the next 48 hours. So without further delay, I'd like to introduce Solomon Chang.
And good morning, good afternoon, good evening for those of us joining from Europe. And welcome back for those of us who have participated in the previous webinar by the Gun Company on electrical insulating materials. This webinar takes the previous webinar to a higher level because we will be talking about comparisons of electrical insulating material properties. So why do we want to compare material properties? There are many good reasons. And the first one is material alternative. In the last 2 years, or 3 years, we always run into material supply chain issue. And from time to time, purchasing department would say that they cannot get material A in time, or either the lead time is too long or the material is no longer available. So they want to substitute material B with the incumbent material A. So obviously, we want to make sure that they would not affect our product or components. Sometimes purchasing come to us and saying that for purchase productivity or cost reduction, they want us to look at this material. So we will do the same thing. Sometimes customer want to, or ourselves want to improve the properties of certain components. So again, we would need to compare the properties of the incumbent material to the candidate material we want to replace with or add as an alternative. So those are all good reasons for comparing material properties. And in order for us to compare material properties, we obviously need to know the material standard and the test standard and the relationship. And besides looking at a single number, we also like to look at what we call the graphical test data, the stress to strain curve. I will elaborate on this later on, but this is essentially the behavior of the material under stress, and that's very important for mechanical properties. We also like to look at how the material fails. It tells us a lot about whether the design will be successful or with good reliability in the long term. And nowadays, we just don't look at one number alone. We need to look at the statistical significance of, especially in comparison, when we compare two sets of data. Are they different? If they are different, is it statistically significant that one is better than the other, or they are equivalent? And on top of that, at the end, after we have compared the material properties, we may want to use the candidate material and make some actual components or even finished product. And then at that point, we are talking about application testing, testing incumbent, design to candidate design, and we need application testing, and we need special test method. Without a good understanding of the material and test standard of the material, we would not be able to come up with a test method that's valid and that's meaningful. So those are all the reasons why we want to compare material properties. This webinar will be focused on mechanical properties of electrical insulating materials. The reason why is because mechanical properties for electrical insulation is as important as the electrical properties of the insulation, and sometimes even more important. And it plays a very important role in successful product design, safety, performance, and reliability. And at the end, these are the three takeaways I hope we can take with this webinar to have a better understanding of mechanical test standards for electrical insulating materials and how to avoid improper comparison. We want to compare apple to apple, not apple to orange, to get the results or the conclusion that we need. And now, after all 1 and 2, then we want to learn how to customize non-standard test method. Sorry for the typo. And non-standard test non-standard test method is what I talk about, application testing. That is specific to the product or the application. Before we start, we would like to send out a poll. Okay. So I just talked about material standard and test standards. What are the most popular material and test standards? In North America, we are talking about NEMA, ASTM, UL, and ANSI. Internationally, and in Europe, we are talking about IEC and ISO. Up until the 1980s, it's the US military that come up with, that control the material standard for insulating material. And many of you are familiar with the MIL standard, MIL standard. And in the 1980s, US military decided to get out of standard maintenance and asked NEMA to take over. And that's why the NEMA LI1, the standard for insulating material, especially rigid thermoset laminate insulating material, is very popular. And the NEMA material grade like GPO3, G11, FR4, G10, they are in millions of drawings. And when you look at some of the a lot of the drawing, under material call out, it will just say GPO3, NEMA, sometimes say NEMA GPO3. ASTM, okay, NEMA standard is a material standard. It does not, it refers to ASTM and sometimes UL for the test method. And everybody know about ASTM. They are the standard for testing, especially on mechanical testing. And UL, again, everybody know about UL. UL 94 flammability. That is like the golden standard for especially plastic or polymeric material flammability. And those are what NEMA LI1 or the updated IM 60000 refer to. And we also have ANSI in North America. I think it covers Canada and Mexico also. And ANSI do not publish its own standard, but it recognizes other standard organization standard as long as they follow the ANSI guideline in the standard development and preparation. Essentially, standard development and maintenance need to involve the user, the consumer, the manufacturer, the public, outside expert like university professor or outside lab. And the whole idea is to make sure that the standard represent the interests of the industry and the public, not one or two companies. So if you see an ANSI stamp on a standard like ANSI UL this, ANSI NEMA that means that standard has been approved and recognized by ANSI. IEC and ISO are international standards. ISO was set up by the United Nations in 1947. It is the standards of every standards. And many of us are familiar with ISO 9001 quality, ISO 14000 environmental health and safety. And for electrical standard, ISO refer back to IEC. And IEC standard for electrical insulation, when it comes to the mechanical section, refer back to ISO. And then the ISO standards, from a lot of it come from BSI and British Standard Institute, and DIN, the German standard. So if you look at a drawing and it has BSI and DIN in it, chances are it is an older standard, and you can always trace it back to the corresponding ISO or IEC standards. And again, I would like to send out an poll.
Yeah, standards poll.
Mm-hmm.
We're going to pause for just a minute and fix this taskbar on the bottom of the screen. Go ahead and complete the poll, please, and we'll fix this taskbar at the bottom.
Background.
You can select more than one standard on that poll, I believe. Oh, no, you can't.
It's gone? Okay. Thank you. Okay, thank you, Josh. Looks cleaner now. Okay. So looks like many of us, especially UL, we all know about UL and NEMA. Yes, as expected, IEC is an ISO. They are, because the audience obviously is North American based, but there are enough of us who work with international standards. That's a good thing, because I'm going to talk about the difference between IEC and NEMA standard a bit later. So these are the requirements for a good test method or good test standard. Essentially, a good test methods, and I would say ASTM is very good at all this. The standard, the test method must provide meaningful results for use and be repeatable intra-laboratories and inter-laboratory. That means if you have the same set of sample, you test it 2 or 3 times, it should provide consistency, the same result within a couple of % by the same laboratory. And then if you take that material and send it to a different lab, if they follow a good test method, the result should be similar, again, within a few %. Actually, ASTM tells you the inter and intra-laboratory uncertainty for each one of the test method. That's why I said ASTM is a very good test method. And again, before I continue, I'd like to send out an poll and see how familiar we are with testing. Okay. Okay, great news. I'm talking to the expert, so I better be careful. So most of you, obviously, based on the response, have seen it. This is the NEMA LI1 or IM 60,000, section 22, and that's the NEMA G11. And that's the performance requirement table. That's a very important table. First thing, it'll tell you what is the test standard. And then it'll tell you what conditions the test coupon has been exposed to. And for high temp material, which is G11, is a high temp glass epoxy grade, it will tell you what's expectation at what they call elevated temperature property. That's to test at 150 degrees. And it also shows you the properties for different material thickness. As you can see, some properties are thickness dependent, some properties are not, but NEMA show it all in one table. For those of you who have worked with IEC standard before, this is the equivalent 60893-3-2 epoxy, glass epoxy. As we all know, there are different grades of glass epoxy, FR4, FR5, G11, G10, G11, G12, G13 now. With NEMA, each one of them has its own section. With ISO, they put it all under -3-2. So you have to recognize, okay, G11's equivalent EPGC 203, and then you look across, okay, it tells you the test method, and then you look across for thickness. It says greater than 1.5, greater than 5 millimeter, but then you say, hey, some property are thickness dependent. Okay, IEC would ask you to go to a different table to look at property that are thickness dependent. And then for elevated temperature material, like the 4 on the right-hand column, and that's superscript 1. That means you have to read the remarks. The remark tells you that for elevated temperature, supposed to be half of the specified value at room temperature. So this is essentially a quick comparison between the NEMA and standard on material properties and IEC standard on material properties. I know I'm a bit biased, but I think the NEMA one is easier to understand, and then you have to flip back and forth through different documents. One thing that we did with the NEMA IM 60,000 is to provide SI unit on all the properties. And we went through an exercise and actually compared the NEMA properties to IEC properties. As far as the actual value is concerned, they are within a couple of percentage points. So they are in agreement. So, and most of them can be converted readily. Not some of them, I won't go through them in detail. It's like water absorption. NEMA and IEC use different philosophy, how they want to express water absorption. The same goes for impact. And then the one beef that we have is the IEC definition for elevated temperature mechanical properties. As you can see here, with NEMA, it's very clear. At room temperature, it flags is 60,000 psi, and at elevated temperature, it's 30,000. So roughly half. That's what IEC said. Okay, but then IEC put it in the remarks, and then sometimes people can construe that instead of saying that it's half of the requirement at room temperature, some people are saying that it should be half of the actual test value at room temperature. So material that outperform at room temperature would end up having a higher bar to meet at elevated temperature. For example, IEC EP GC 203, 340 MPa at room temperature, so that means 170 at elevated temperature. But if your material tests out at 600 MPa at room temperature, some people may argue that it has to be at least 300 MPa at elevated temperature. That is not the intent of IEC. The gun company actually holds a plenary meeting of IEC TC15, which is responsible for all this. And we talk about this at the next revision. We will add one more sentence to the remark. Say, for example, 340 at room temperature means 170 at elevated temperature. Example like that, we clear a lot of discussion or argument between purchaser and producer. Now, there are 5 main mechanical properties we will discuss in this webinar, and they are in this order. The reason why they are in this order is that 1 and 2 and 3 are almost a requirement in the majority of the NEMA and IEC material standard. Tensile is usually, you can find tensile as a typical value. And shear, again, as typical value. And NEMA only lists punch shear. IEC lists both parallel shear or ILSS and punch shear as typical value. And for those of you who have attended a previous seminar on electrical insulating material properties, we talk about the difference between requirements and typical value. In order for material to be recognized as a NEMA grade or IEC grade, it must meet the requirement. The properties must meet, all the properties must meet the requirement. Property that has a requirement are always shown as minimum or maximum. So you need to exceed the minimum, or you cannot go beyond the maximum. Those are requirements. You must, or else it cannot be recognized as a NEMA or IEC grade. Typical properties are, okay, I won't use the word optional. Those are the argument like you should. What it is that those are the properties NEMA and IEC has enough historical data to publish it, but then they don't want to, or the lawyer told them not to call it an absolute requirement. So you can find those as typical values. And before we move on to talk about those 5 properties, I'd like to talk about the universal testing machines. And based on the response, most of you are familiar with universal testing machine. They are universal because they can test everything that I talked about before, except impact, plus a lot more. But they are universal in what they can test. They are not universal in the range. And as we all know, insulating material, the mechanical property can vary by degrees of magnitude. Thin gauge material, flexible material, they are obviously not as strong as thermoset laminate. And heavier raw material are stronger than thin raw material. So the gun company, we have a universal tester as low as 1 to 1,000 pound maximum. Those are the one we use for flexible materials, some thermoplastic, paper. Most composite material can be tested with a 20,000 pound or 20 KSI universal tester. But when you get into heavy wall stuff, 1 inch wall and above, then obviously you need more poundage or the tonnage, like a 120,000 pound or 60-ton machine in order to perform the testing to failure. One thing about the universal machine is that nowadays they're all digitized and they are very sensitive. Their load cell can be as accurate as down to 1 pound. And then the displacement, the universal machine tests both the load and the displacement of the coupon, and they can measure down to a fraction of a Dow or less. And the reason why it's important is because we need to know about the stress, strain to stress behavior of the material under test beyond that of just having a number, how much force it can withstand. And this is a typical stress to strain curve obtained from a universal testing machine. And this is a ductile material, probably copper or brass. And as you can see, initially, there's an elastic deformation region. This is linear. And also, once you let go of the stress, the material will go back to the original dimension. So this is the elastic deformation zone. But it doesn't last forever. Once you exceed a yield point, then the material starts to elongate without a lot of increase in the stress. And it will strain harden, it will neck, and then it will fail, crack, or be broken apart into two pieces. And the universal testing machine, the moment a fracture or failure occur, there will be a drastic drop in the stress or the load, and the universal testing machine will stop right there. And that's one very important parameter we can get from a UTM. It's a linear zone where the slope, essentially the rise over run is the slope, and that is what we call the Young's modulus. Why is the Young's modulus important? Nowadays, we all do finite analysis. The Young's modulus is one number the finite analysis require. So this is, and most of us are familiar, the Young's modulus is usually a very large number, like a GPA or MSI. And the reason being that because it's divided by elongation in a small fraction. So the rest of them just repeat what I said about the elastic zone and plastic zone. So now that we learn about the universal test machine, we would like to go into the 5 properties. Okay, first one is flex or bending property testing. And flex is very important for both comparison and also design. If you have two material substitution, if you do the flex of material and compare to A to B under the same condition, you already know a lot. And also the flex data can be used in design work like the finite analysis that we talk about. Okay, flex seems to be simple, but in order to do it correctly and get the right number and arrive at the right conclusion, there are certain things that we need to watch out. The flex is essentially a 3-point bend. Sometimes people call it a 3-point bending test. The coupon or the specimen is supported on both ends, and we apply a force in the middle. And this explains what happened when you press it down. At the bottom, there's a tension. The material being stretched, so there's a tension. And then at the top, the material is being compressed. There's compression. Ideally, in the middle, nothing happened because the material neither elongate or being compressed. And in order for you to get the actual flex failure, you have to look at the coupon. If the test coupon upon failure look like the pictures above, and that is not a flex failure, that's an interlaminar shear failure. The material actually shift between layers. A real flex, so that doesn't count. So the reason why it doesn't count is because we do not have the adequate span distance. ASTM and ISO call for a 16:1 span distance. 16 is the distance between the two blocks, and then the 1 is the material thickness. If it's less than that, then you could run into ILSS failure. And for material with weak ILSS, sometimes you need to increase the span distance beyond 16:1 to get a proper flex failure data. And a UTM, the the flex test, the stress to strain curve on the UTM would look like that. The bottom one, the C, is a ductile material that I shown before, and the top one is brittle. Again, with brittle, once you are beyond the linear elastic zone, the material will fail very rapidly. It would not hang in there. And ductile material would hang in there more. Copper and brass are ductile. Unfilled thermoplastic are quite ductile. Once you start filling it, then it will become more like B. And B is in between brittle and ductile. For the thermoset composite that we use for mechanical support because of its strength, it's usually between A and B. It's not super brittle, but it's on the brittle side. And for brittle material, because it failed, because it then the fail point is where the material fail, and the universal tensor UTM will pick up a fail point. For ductile material, because it doesn't fail, then ISO or IEC say stop it at 3.5%, and ASTM says stop it at 5%. And in that zone, really doesn't make a lot of difference whether 3.5 to 5% elongation. Essentially, they just want to have a standard where we stop the testing. The second important properties is compressive. That is, again, very useful to compare material A to material B. It is also useful for design work. Again, here are the stress to strain curve from the UTM. Brittle is number 1, ductile is number 4, and the middle one are in between. And also, if it's a brittle material, when it fails, it's an axial crack right down the middle or diagonally. That shows a brittle material failure. A ductile material, if you compress it, it actually expands a little bit and looks like a barrel. And and there's a Poisson ratio that talk about the displacement in the y direction to the compression in the exact dimension, but we won't cover that in this webinar. But that is a very important number for the finite analysis also. But the failure mode is not a vertical crack or diagonal crack. It's a lot of minute failure. So just by looking at the coupon after it failed, you can tell whether it's ductile or brittle material. And this is a picture of how we conduct compressive testing. Again, very simple. As long as you follow the rule on the sample, it should be a prism, 1/2 inch by 1/2 inch by 1 inch in length. And for tubes and rod, just follow the rule. And again, when you compare the properties of material A to material B, and it shows some compression, then you have to make sure that the property are performed using appropriate ASTM or IEC, ISO method. So there's apple-to-apple comparison. Okay, so even though it looks simple, both ASTM and ISO method want you that you have to avoid, you have to make sure that the space, the coupons are properly aligned. A good UTM is self-aligning. If the alignment is off, especially with tensile, you get bad result. And for compressive tests, you have to make sure that the surface that face the platen is perfectly flat. On the left-hand side, it shows a protruded spacer. With protrusion, that's always the top and bottom die, and in between is your parting line. Before you test it that way, you had to make sure you had to sand off the parting line so that you don't localize all your stress on the parting line, and that gives you premature failure. Those results don't count. Impact. Most IEC or NEMA material standard shows impact properties. And in most cases, those are not very high bar. And I have not seen thermoset composite having trouble passing impact property, but it's there, and it's good for comparing material A to material B as far as whether one is higher than the other. It's not very useful for design work, but it's a good comparison between material, and they are not done by the universal test machine. They have special tests, essentially you swing a pendulum against a coupon and see how much the force the coupon can, how much energy, in this case, the force can, the coupon can absorb before it breaks. And okay, with UTM, we can look at the stress to strain curve and see if the material is ductile or brittle. In this case, we don't have the UTM, but we can always look at the sample after it failed. The brittle one is on the left, it just broke into two halves. The ductile one, you can tell it's kind of absorbing some energy, so it hangs in there for a little bit until it failed. So just by looking at it, you can tell whether the sample or the material is a ductile material and or brittle material. This one, I think one of the reasons why NEMA or IEC do not put it into their spec as requirement is that this is one properties a design engineer trying to avoid as far as the insulating material is concerned, because rigid thermoset laminate, the insulating material used for mechanical support, they are always stronger in with flex and compressive strain than with tensile. So most design engineers will want to make sure that the insulating material is not under tensile stress. So this property is obviously very important for design work. And again, the test coupon shape is on the left-hand side. It is a dot bone shape to facilitate stress localization. And also, this helps with the alignment, because as I mentioned before, one thing about the universal tester is that a good one with good fixture will help to align so that the force is applied in 90 degrees rather than twisted. And the stress to strain curve looks like every other stress to strain curve. There's the brittle one is on the left and the ductile one is on the right. And with tensile, if it's a tender ductile material, it can elongate a long way before it breaks, like picture A on the right-hand side. That shows a very ductile material. On the other hand, a brittle material is C. It just broke. The last one, not as popular as the other four, but it's important for design work, not just the product design, also the manufacturing method. Say if we are punching some heavy gauge thermoset laminate, then we better want to make sure that our press has enough tonnage to do the job, and that we can use what we call the punch shear strength. And a punch shear is to the top left-hand side, essentially. That's what it is. We apply a force to punch through perpendicular to the lamination. So we find out what that is in PSI or KSI, multiplied by the total shear area of the component. And then we know what kind of press, what kind of tonnage we need. Obviously, we need a safety factor. ILSS or in plane or parallel shear or interlaminar shear is different than punch shear because it is in the same direction of the lamination. And essentially, it is the force that's holding thermoset laminate layers together. And it is important as I have a good example later on. The one thing want us to remember is that the ILSS is usually 2 to 3x weaker than the punch shear strength for thermoset laminate. And that is a very important consideration for product design. If possible, we try to avoid our components to be under ILSS because in a way, that's the weakest part of the thermoset laminate. And ILSS can be obtained using ASTM method plus the IEC method, and they use or even customized test method, but most of them require special fixtures. And there's also a quick way to do ILSS. It's essentially a 3-point flex test, but then you reduce your span distance to something like 4:1, and you be essentially force the coupon to fail in the ILSS manner. So it's a quick way. I mean, if you don't, for screening tests, if you want to compare A to B and you don't want it to go into the more elaborate ILSS, then you can use the 3-point bending. One thing why ILSS is the weakest part of thermoset composite is because it is influenced by the bonding of the resin to the fiber. So if the fiber has void and porosity in it, then you can see that it will be weak on the ILSS. Now, in summary, we talk about mechanical property comparison. So obviously, the conclusion is that materials standards should always test reference test standard. If you see a technical data sheet, give you all kind of number without any test standard, it doesn't mean anything. And also, we talk about the US and international standards. And one thing that I like to highlight, and nowadays with Minitab being available, in addition to just looking at one number against the other, we also should apply some statistic to it, especially when we are talking about property comparison, because the statistic would be kind of impartial, telling us that whether A is as good as B, or B is worse than A, or B is better than A when we compare material. And now, as I mentioned before, after all the material property comparison, if we are still in doubt whether substitution can be used, then we are talking about customized application testing. And I have a few examples at the back. And the gun company, if you want us to help you with customized application testing, just talk to our sales engineer and our account manager, and we can help you out. That is just a statistic from Minitab. So, for example, in a material substitution situation, not only that we compare the properties of the candidate to the historical result of the incumbent, we also test the incumbent and the candidate side by side. We use the same aging, we use the same conditioning method, and we use the same test method. And then once we all those results, and then we can apply statistics and ANOVA testing to see if we are indeed seeing a difference or it's just natural variation. Now, if you want to find out more from us about material properties, comparative material property application, just go to our website or scan our QR code. And one of the QR code, I think the bottom one, if you scan it, the first one will give you all of our material data sheet. The second one will give you material comparative data sheets. And then we divide it up by market. We have 5 different markets. So pick the market you choose, and then you can see the material comparison by NEMA grade, equivalent, IEC grade, what's the generic name, and every properties that you want to know. Okay, so to conclude the seminar, I have 5 slides about special application testing. The first one is our standoff insulator. And this is what we call the cantilever testing. And as we all know, these are standoff insulators. They are used to support bus bar, and during short circuit, there will be, the bus bar will have a tendency to move, and we want to make sure that they have enough cantilever strength to prevent the bus bar from moving in case of a short circuit. It's a safety. And the second one, again, is a safety test. This is a fuse strip holder. And what we did is when the trips fuse strip, during the overcurrent situation, the fuse link will fail, and then there will be a plasma. We want the fuse strip holder to be strong enough to hold the plasma, and that's why we apply this test. And this test essentially turn the compressive force on very highly viscous liquid into a bursting force, and depending on the type of the fuse, there are requirements that we need to meet so that we know the fuse can withhold the plasma plume in a failure situation for safety. And also this test also detect delamination. So if the filament wire tube or common wire tube used in the fuse strip holder was not made properly, it will fail in the delamination before actual burst failure. So that's why that's an example of failure mode being useful. Won't go into this one too much. This is the dot bone. We call it a transformer spacer. What it does is that it provides support during the winding. And more importantly, in application, it provides a channel for the natural convection, so cooling. So that's why it's a dot bone shape to provide additional cooling channel. And some customers apply it one way, flat right. Some customers apply it the other way. Some customers apply it in the direction A. Some customers use it in direction B. So, and the customer want to know how much compromise in direction B is in terms of the compressive strength. So we test it for the customer using a non-standard compressive test setup. This is what we call slot wedges. It's used in generator and large motor stator. Essentially, it keeps the winding underneath in place. And in a generator or large motor, there's vibration, and also the on-off the cycle that produces a lot of thermal stress. So the coil, the winding, want to pop out, and the wedge is holding it in place. Obviously, it's serve a very important function. So we want to make sure that it has the proper shear stress, and that's our special testing devices. This one could be interesting. We talk about ILSS, interlaminar shear stress, and how important it is in application. Top left-hand side is a thermoset laminate. So we want to drill a hole in it. If you drill a blind hole, you actually can introduce ILSS. If you want to drill a hole, drill a full hole so that you don't introduce ILSS. And also, drill it perpendicular, don't drill it parallel, don't drill it sideways. I mean, you can imagine if your drill is down and your drill is too large, you will split the material right there and then. Even if you are successful and you have a thick material, you manage to drill a hole in it, and then you use it to hold the bus bar, it does not have the strength to prevent the bus bar from moving during a short circuit failure. And that is a problem. I mean, that's the opposite problem. And the solution, I mean, that's the actual example. The solution was very simple. Just change the direction of how you machine that spacebar, that spacer and bus bar holder. Same apply for tubing. Drill it full. And the gun company, we are capable of performing all these tests and plus other mechanical tests. So again, if you need us, just call just talk to our sales engineer or account manager, and we can even custom design some end product testing if you want to go beyond just mechanical testing for comparison purpose. Okay, sorry for the interruption at the beginning. I think I managed to finish 5 minutes.
Yeah, no problem. Thank you, Solomon. And for those that are here today in attendance, we have the links to those handouts, as comparative data sheets that Solomon was talking about in the chat, and also you can go to our website and find those comparative data sheets. And as we're getting ready to answer questions here, you can ask your questions in that QA pane, and we can begin to answer those. We do have some questions that we received prior to the webinar. We do want to, before you take off and leave today, we would like to launch a quick poll and get some feedback. So we will launch that just to see how we can improve and how we're doing. So let me just check and see if we have any questions in here. Okay, right now, no questions in the QA. You can also raise your hand, and we will check we will unmute you, and you can ask your question directly to Solomon if you have questions about any of the materials or topics that we've covered, or any other topic that you think we can try to help you with.
Yeah, any topics in the future that you want to.
So Solomon, I'm gonna go by some of the ones that we've actually already got here, just to get us started here for today. So Jim had asked, can TGC test tear strength of papers? Jim is apparently working with some papers, so he wanted to know if we can test tear strength.
Definitely. It can. Our low-range universal testing machine go down to 1 pound, and a lot of tear strength are in the 10 or 20 pound range. So we can do it with a very high degree of accuracy.
Yeah, and there's a couple different test methods for tear strength, I think.
Yeah.
But if I remember right, TAPI is one of the.
Yeah, Appendorf. I mean.
Yeah, there's some different test methods there, so you may have to decide on the right test method. But
and we have the fixture to cut out the coupon to the different test requirement.
Okay. Let's see. Looks like we have any questions in the QA pane? Okay. Anyone raising? Oh, I don't want to raise my hand. Anyone raising their hand right now? No one wants to talk to you, Solomon.
Okay, go ahead.
Okay, so I'll take another one that we had received. So one of the questions was, what is the thickest piece that, this was from Steve, actually. What is the thickest piece that can be tested for compressive strength?
Okay, so if you want to do it the ASTM or NIM array, I think they ask you to machine it down to 1/2 inch or 1 inch. But then if you want to test it as is, then we can use the large machine to our right-hand side. So if we test a 4-inch block, that is not NIM, that's not ASTM or IEC method. But for comparison, we can do that.
Yeah, and I think we just had a very similar example come up with a customer recently, where they're they're using like 2-inch thick material or 50 millimeter thick material, and they wanted to test that material, but it's not going to be a standard result if you use that thickness. So, you'll have to probably machine that down to the standard thickness, which, in that case, I'm not sure you're getting a result that you're looking for anyway.
Yeah.
Okay, let's see. Any questions in here? Okay, from David. For materials that can be oil immersed, do you test the wetted version? Are you testing an oil? So, David, if I understand you correctly, you're asking if you can oil soak or condition the samples prior to testing them.
Yeah, I mean, again, it may not be a standard. It may not be a standard test, but nobody can stop us from doing custom testing, especially you want to compare material A and material B, and we just did a lot of testing on vanished flex material, and it may not be a standard test, but
Yeah,
for comparison, it's perfect.
Yeah, David, and we actually have a couple of instances where we've done press board and wood materials like this, where we actually will have those impregnated with oil prior to doing the testing. So yes, that does make a difference, and we do the before and after testing on that. That's a good question. Thank you. All right. Anybody else on our raising their hand here? Okay. And I got one other one here, Solomon, from Andrea, who asked if we can do coefficient of friction testing. I'm not sure if that's a mechanical test. I guess it is.
Yeah.
Coefficient of friction testing, the gun company.
Not right now, but we have a laboratory in North America and in China that we have used, and they provide very reliable and very fast turnaround on. And it's SGS Shanghai, and they are very, very reputable laboratory.
Yeah. And I think if you're just looking for simple roughness checks, like some comparable roughness test or something like that's a pretty simple test. But if you're looking for an actual coefficient of friction test,
0.12, 0.15,
that could probably be something we would contract to a third party. Okay. Any other questions? Let's see. Got anything else in the queue? Oh, here we go from Joshua. Oh, an abrasion resistance test, very similar, but yeah, is there an abrasion resistance test for testing for electrical materials?
We actually have done some using a modified ASTM method. And yes, the answer is yes, but we have to look at it in more detail.
Yeah. Might want to look at exactly what kind of abrasion you're looking at. I'm not sure we did that for an electrical application.
Not yet.
More mechanical. But yes, there's abrasion resistance. I don't know that I recall anything being listed for electrical materials, but it's definitely something we've done for composite materials. Yeah. Hope that answers your question, Joshua. All right. And let me just make sure there's no hands raised. Okay. All right. Well, I think if that's all the questions we have for the day, I want to again thank Solomon for today's presentation and thank everyone for attending. And we appreciate you being here. Please feel free to contact us via email with any other questions, or you can give us a call. We'll also have a follow-up email in 48 hours with the link to today's recording. On behalf of the gun company, our presenters, thank you for joining us today, and we hope to see you next time. Have a great rest of your day.
Thank you.